When last we met, chapter 11 is hypothesis test and inference part 2 or 3 or 4, whatever part you want to look at. Basically, chapters 9 through 13 are all about inference. Inference is all about hypothesis tests and confidence intervals, interpreting it. Inference is basically 40% of your AP Stats exam. And it's kind of what I've been talking about all along here, which is why we do statistics. We sample from a population, we look at our data from that sample, we look and kind of apply normality if we can check for some things, and if we've done things correctly, then we can take the information we gain from our sample and apply it to our population. And that is what inference is. So, at this point, we've done our one sample t-test, we've done our one proportion z-test, and then last week we looked at 2 samples, and the big difference for the 2 sample one was, were they independent, or were they matched or paired? And that's really the hard part when we're dealing with 2 samples. Okay? And we talk about matched or paired. When you matched or paired, we're looking at the difference between them. And if they're independent, we're looking at the mean of one minus the mean of the other one. Okay. So that's what we're looking for, and that's what we did last week. We're going to close out chapter 11 right now, and we're going to go into 2 proportions. And this was obviously t-tests over here. This is now going to be a 2 proportion z-test. Same 8 steps, same random independent normal. In this case, since we have 2 proportions, you need to justify a sufficiently large sample by doing it a total of 4 times. I'll explain that when we get there. But I think you're going to find that it just flows very similar to the next step that we should go to. Some messy formulas, not messy formulas, I guess that's the wrong way to say it. We have this thing in the denominator of our statistic, which is called p hat c, and it's the combined. Okay? P hat c combines the 2 proportions. That will not be given to you on your AP formula sheet, nor do I expect you to memorize it. It's there. You can plug it in and find it if you needed to. Your calculator will tell you what p hat c is when you do the hypothesis test. Now, a big difference between the z statistic when you're doing our hypothesis test and when you're creating the confidence interval for a 2 proportion. When you're looking at the confidence interval, you will keep them separate. I'll say it again. When you're doing a confidence interval, you will keep your proportions separate. When you're doing the hypothesis test, you need to use the p hat c. Your calculator will give you the p hat c. You'll plug it in the appropriate location. When you're doing a confidence interval, you will keep your proportions separate. Does everybody see that difference that I'm talking about in the 2 formulas? Because part of your setup for these procedures is write the statistic dry, then plug in the right things at the right location. That's what we use as teachers and your AP graders as you demonstrating that you know what you're talking about. Okay? At this point, like I said, confidence intervals and the 8-step hypothesis test should be very much probably flowing, and you guys should probably be tired of it at this point. Okay? Give you guys a second. I'm just copying those down. Let's see. First example. Let's see again. Public Agenda conducted a survey of 1,379 parents and 1,342 students in grades 6 through 12 regarding the importance of science and mathematics in the school curriculum. It was reported that 50% of the students thought the understanding in science and having strong math skills are essential for them to succeed in life after school, whereas 62% of the parents thought it was crucial for today's students to learn science and higher level math. The two samples, parents and students, were selected independently of one another. Is there sufficient evidence to conclude that the proportion of parents who regard science and math as crucial is different than the corresponding proportion of students in grades 6 through 12? Test the relevant hypothesis using a significance level of 0.05. Okay? Two things, again, for hypothesis test. They tend to tell you what it is they're looking for. It's usually explicitly stated somewhere in the problem. In this case, we are looking for, is there a difference? So proportion of parents who regard science and math as crucial, is it different than the corresponding proportion of grades 6 to 12? Is different. That's big words telling us this is a two-tailed test. We're looking at not equal to. It's not asking us if the proportion of parents is greater. It's not asking us if the proportion of parents is less than. It's asking, is it different? So that tells us it's a two-tailed test. It's very specific in the context of this problem that we are talking about proportions here. And we're going to use our 8-step hypothesis test. Okay? Step 1. Identify your populations. In this case, we're going to call P1 equal to and P2. We have two proportions. So P1, we're going to call that the true proportion.
Way to go, Ben. Oh, yes. No more notes.
Oh, there we go. True proportion of, what is it, parents who believe that science and math is essential. So science and math is essential for future success. And P2, that's the true proportion of students, grades, was it 6 or 12, who believe science and math is essential for future success. Okay? Should be clear to you that this is going to be a z-test, not a t-test. We're talking about proportions. Our null and alternative. It says we're testing for a difference, so I'm looking at P1 not equal to P2. And then my null hypothesis is that P1 is the same. So I'm going to hypothesize that the proportions are the same unless I have evidence to say that the proportions are different. Again, you can write it in this manner. Another way you could write it is P1 minus P2 equal to 0, and P1 minus P2 not equal to 0. Both of those say the same thing. Pick one or the other. I don't care which one you do, but if you have this one, keep it at that one. If you have the right-hand side, keep it at the right-hand side. You're welcome to list both of those there. They say the same thing. Let's see. Our alpha level, 0.05, I believe. So we're looking at 95% confidence. Yeah, for step 1, you do need both P1 and P2 with two proportions. Yeah, next step. Identify this is a two proportion z-test. Let's see. I believe it did say random sampling. Is that correct?
Yes.
Did it said independent? I don't know if it said random. Did it say random? I caught the independent. Yeah, I didn't see the random though. Anywhere? So, assume survey was random. Bless you. And I'm just going to kind of do it for population 1 and population 2. So, assume sample or survey was random. And again, you can just write one sentence and say, instead of kind of doing it like I'm doing it, you're welcome to write a sentence and say, I am assuming that the survey was given to a random sampling of parents and a random sampling of students. It's given to us in the context that it was independent, so independent sampling is present, or just say is given in the context of the problem. I'm not going to write that one twice, but it applies for both of them. And now sufficiently large. Both cases you have to demonstrate sufficiently large. So we have parents at 1,379 with 62%. So parents was population 1, 1,369 times 62% is greater than or equal to 10. 1,369 times 1 minus 0.62 is greater than or equal to 10. And then the other students, we're looking at 1,342 times 0.5 is greater than or equal to 10. 1,342 times 1 minus 0.5 is also greater than or equal to 10. And then I would show that, check it out if you want, and I'd say both samples are sufficiently large. So central limit theorem applies. We can apply normality to this sample. Okay? Again, random, independent, and normal, just do it for both populations.
So every time if samples are sufficiently large, then we would also say the central limit.
Yeah, you can apply the central limit theorem. Because the central limit theorem says if your sample is sufficiently large, regardless of what your population looks like, your sample will be approximately normal. And if your sample is approximately normal, then we can apply that normal distribution. Which is why we're going to be able to z-score it, or why we're going to use the t-distribution for it. Okay. Next step. Our z statistic is going to be p hat 1 minus p hat 2 minus, and that's p1 minus p2 over the square root of p hat c 1 minus p hat c over n1 plus p hat c 1 minus p hat c over
P hat minus P hat minus 0.
In this case, we've hypothesized that it is 0. It might be different. We might say, is it different by more than 3%?
Okay,
And then
if it
it-
doesn't
then it
say
would
that,
be-
then I still write 0 instead of 1.
Yeah.
Thank you.
Yeah, PC. The other one's a math. Go ahead and substitute in what you know so far, which is going to be 0.62 minus 0.5 minus 0. In the original formula I gave you, it was 0 automatically. Question came up, what if I don't write that P1 minus P2? Here's the deal. Both what we covered last week was independent and matched or paired. The examples that I gave you in class was the difference is 0. In this case, We're also hypothesizing that the difference is 0. Different wordings will give you a different value for this difference. If there's something like, is there evidence to say that there's more than 3% difference? You see how that's different wording. 3% difference, then your null hypothesis is going to assume that it's 3, and then not equal to 3 if there's not a 3% difference. Or is there greater than 3% difference? So that's going to be equal to 3. This would be greater than 3. And then down here, that difference would not be 0. Instead, it would be 3. Does that make sense? Okay? So keep an eye out when you're looking at those problems. I think there's a couple problems in your homework that will have not a difference equal to 0. Okay, let's go ahead and go to the calcs. Stat, test, 2-prop z-test is what we're doing. Go ahead and plug in your data. Let's see if we put in parents as P1. So parents, that first one's going to be 0.62 times, what do we got there? 1,379. That's not going to work very well.
69.
Did I type it wrong?
Yeah. Yeah, still that's
So what do we have?
1360.
0.62 times 1,369?
Yeah.
Okay. Still decimal. And then N1, we're going to get an error right now, so I'll talk about that in just a sec. Let's go ahead and make that, what is that, 1,300? Is it 69?
Yeah. 79.
I was going to say, I have 79 written down. 79.
But you
You
wrote
wrote
69 on that.
Okay, there you go. That's 79. $1,379 times 0.62 and 1379. The other one's gonna be 0.5 times 1342, and that's gonna be 1342. You're going to get an error. The reason you're going to get an error is you've told them that 854.98 people answered yes, that they think science and math will lead to better education.
Do you chunk it or round it?
I would route this to 855. That's good. I don't, in this case, I would fudge this some. If this is an AP exam question, 854.98, I'd call it 855. Yeah, not equal to. Okay? Everybody okay with that? Z-score 6.3 right away. A Z-score of 6.3 should tell you you're going to have a real small p-value, correct? And 6.3 standard deviations away from average tells you it's a long way from average. Your p-value is very small. Do not report 2.86. As a p-value, report approximately 0, please. Now, your calculator, p hat 1, 0.62, p hat 2, 0.5, you've got that. You've got a third one that just says p hat here. Oh me, oh my, whatever could that third p hat represent? P hat C. Indeed, you are correct. Good job. Congratulate yourselves for identifying p hat C correctly.
You had yourself in the
P hat C, what did we say was 0.52? 0.56. Okay, so 0.56, 1 minus 0.56 over N1, which we said was 1,379, plus 0.56 times 1 minus 0.56 over 1,000, what was it, 342? Okay, which yielded us a z-score Z equals, what was it, negative 6.3 something? 0.56, because that's P hat C. And again, to get your p-values, you norm CDF that 6.306, comma 100. It's going to be essentially 0. P-value is approximately 0. Finishing it up, show p-value less than or equal to alpha value. So 0 is less than or equal to 0.05. That's going to give us a reject the null hypothesis. Any questions at this point, or is everybody just kind of going, okay, this is motoring through stuff we've already done? Okay, conclusion. At the 95% confidence level, there is sufficient evidence to support the claim that there is a difference between the true proportion of parents and students who believe the value, what is it, value, what do we define it as? What was it, value?
Math and science is essential for future.
Math and science is essential for future success. Is essential for future success. Again, there's your standard 8 steps. Realizing in this case, all we've demonstrated is that there's a difference. You guys probably, personally I agree, I think a better hypothesis test in this situation would have been, do parents have greater value? In other words, is the parents' proportion greater than the student's proportion? Does that make sense? I think that might be, all we've discovered, or all we've kind of claimed here, is that there's a difference between the way what the students think and what the parents think. Do you guys agree with that? And that kind of goes without saying, any way, you know what I'm saying? So if we actually did, can we demonstrate that the parent's opinion is greater than the student's opinion? That would now be a one-tailed test. We would probably also, I can guarantee, we'd also get a p-value of 0 there, because it's such a small, there's such a big difference between, say, 62% and 50%. Do you guys agree with that? 62% versus 50 when you have asked over 1,000 people, 1,000 parents and 1,000 students, that's going to be a statistically significant result. Make sense? All right. You guys. Drug Viagra has become quite well known. It has had a substantial economic impact on its producer, which is Pfizer Pharmaceuticals. In preliminary tests done for adverse reactions, it was found that when 734 men were treated with Viagra, 16% of them had headaches. Among 725 in the placebo group, 4% experienced headaches. These results were provided by Pfizer Pharmaceuticals. By the way, studies like this must be done when drugs come out onto the market. And remember when you guys, because I've seen you, I would imagine you guys have all seen the drug commercials on TV. Yes? Okay? At the end or in the small print, when it says yes, this is indeed, it's really funny to me when I see the ibuprofen ones or the headache ones. One of the side effects for ibuprofen and headaches is that you may have headaches. I had a headache before I took it. So anyway, they do have to publish these results. It is side effects. They've done things like this. That is the fine print. That's the stuff they talk very quick at the end of the commercial because they have to inform you that, yes, this drug indeed is supposed to help with whatever your problem is, but it also might give you other problems. Those problems are called side effects. Okay? So, with this data, what I want to know is there sufficient evidence to support the claim that among those men taking Viagra, headaches occur at a rate that is greater than at the rate for those that do not take Viagra? Use the 0.01 significance level. So you guys go ahead and do a top to bottom, two proportion test on this. Go nuts. Okay. Reject, correct?
Yes, correct.
What, 7.6? Is that what we got? 7.6, 7.6? Okay. Next up.
What?
Next up. It is reported that in 2006, 20% of those in a random sample of 1,112 Americans aged 12 and older indicated that they owned an MP3 player. Oh dear Lord, has that changed? In a similar survey conducted in 2005, only 15% reported owning an MP3 player. Suppose that the 2005 figure was also based on a random sample of 1,112. Estimate the difference in the proportion of Americans aged 12 and older who owned an MP3 player in 2006 and the corresponding proportion of 2005 using a 95% confidence interval. Has the wording been changed here? Okay, so they are asking for a confidence interval. They are not asking for a hypothesis test. Finishing that thought, is 0 included in the interval? If 0 is included, what does it tell you about those two proportions? Okay, so I'll let you guys handle the random, independent, and normal parts for the confidence interval because that's your justification. So I'm going to leave that to you. I will give you the dry formula, and I will let you guys finish it. My biggest point of clarification for you is this. Remember, for this interval, you do not use p hat c. There's no combined. Whereas in your hypothesis test, you actually use the p hat c, which is combined there. Okay? So I'll let you guys do that one. Again, 20%, 1,112 in 2006, 15% in 2005, same number of samples. So go ahead, you guys go ahead and set up this confidence interval. It's a little less intense, there's not 8 steps. You just need to check the big 3. Show me the dry, which I've done for you. Show me substituted in the correct things in the correct places. Give me the confidence interval, please. Give me interpretation on the confidence interval, and then answer this question. Is 0 included in the interval? That's easy. After that, what does that tell you about the change in this proportion from 2005 to 2006? That's a critical thinking piece. Okay? Go nuts. If you try to backwards map this using a hypothesis test, it won't work. But if you experimented with your list, there is, oh me, oh my, I'm shocked to see a 2-proportion Z interval. So I can plug my information in there. Remember, backwards mapping from the test will make it use p hat c. You don't want to use p hat c's for the intervals. They're two kind of different things here. You have to use p hat 1 and p hat 2. On the confidence interval, you've got to use p hat c on the, and I think you had to round a little bit. I think one of them didn't work right. Okay. They both work. Should get something like, on that one, I think I posted it, 0.018 to 0.081, something like that. You have decimals in there again. So check that around them.
Are we done? No, it's just so tedious.